The first thing that should come to your mind when you see a right triangle is the Pythagorean theorem. Because the Pythagorean theorem works on every right triangle. And the way the Pythagorean theorem works is you find the hypotenuse. That's the side across from the right angle. It's the longest side. And the deal is that the sum of the squares of the legs, that would be this and this, is equal to the square of the hypotenuse. Every time.
You lost me. So the 6 and the x equals to c or
Okay. If I take 6 and square it and add it to x squared, it has to equal 10 squared. Not only that, but as long as we're talking about it, if you have a right triangle, what I just said is that the hypotenuse squared will equal the sum of the squares of the legs, a squared plus b squared. But this actually works in reverse as well. You walk into a room, you see a triangle, it's a right triangle, you immediately know this. You walk into a room, you see a triangle, you don't know what kind of triangle it is, but you have the side lengths. If you take the largest one and square it, and then the two smaller ones, you square them and add them together, if they equal each other, then it means it's a right triangle. So this works in both directions. In other words, the converse, this is called the converse is also true. If this, then this. If this, then this. But in this case, we don't have that. We just have this. 6 squared plus x squared equals 10 squared. 36 plus x squared is equal to 100. X squared is equal to 64. X is equal to 8, because I took the square root of both sides. Okay. Then write an equation and determine the value of theta. So this is the hypotenuse. This is the angle we're looking at. So that means this is the opposite side, and this is the adjacent side. And you can now do any one of these equations. The sine of theta is equal to the opposite over the hypotenuse. The cosine of theta is equal to the adjacent over the hypotenuse. Or the tangent of theta is equal to the opposite over the adjacent. And if you have a calculator that does this sort of thing, it's pretty straightforward how to go about it. Okay. Now here I've got 6 over 10. I want the inverse sine. I already know what the sine is, so I want to undo the sine to find out what the angle is. Let's say shift sine, and then in the parentheses put 6 divided by 10, close parentheses, enter. Not only that, but if we did the cosine, shift cosine, 8 divided by 10, close parentheses, equals, hey, it's the same angle. Let's try one more. The shift tangent, so we're getting the inverse tangent of 6 divided by 8 it's still the same angle. So the angle we were looking for was 37 degrees. If you don't have the calculator to do this with, then what you do is you look here, you turn this into a decimal, or this into a decimal, or this into a decimal. This reduces actually to 3/4, which would be 0.75. And you take the chart, and you look in the column sine, cosine, tangent, take your pick, and you go down looking until you find the thing that is closest to, let's say, 0.6 in the sine column. Well, that'd be right here. 0.8, 0.75, 37 degrees. That's how you do it with a trig chart. You just have to know that what you're trying to do is, I've given you the tangent, you have to find the angle. In general, if n is less than k, what's the relationship between the tangent of n and the tangent of k? And it's, if this number, if the degree angle is smaller, then the slope is also smaller, because tangent is slope. That's the relationship. For this problem, this issue is angle relationships, and it's from last semester. When two lines cross, you get a whole bunch of angles, but the really obvious ones here are these two and these two. The ones that are across from each other are called vertical angles, and vertical angles are always congruent. The ones that are next to each other, the adjacent ones, are a linear pair. These two right here, for example. And they are supplementary, so they have to add up to 180 degrees. So you wind up with two pairs of congruent angles, and then four pairs, 1, 2, 3, 4. Four pairs of angles that you know add up to 180 degrees. If you have, and that happens every time two lines cross. Anytime you have a line that crosses two lines or more, it's called a transversal. A transversal is a line that crosses two or more other lines. And of course, at each intersection, you've still got this same thing going on here. Right? The vertical angles are congruent, and the linear pairs are supplementary. These angles and these angles are at different intersections of the same transversal, and that makes them related as well. If you think of this sort of as a nuclear family, you could think of these as cousins. Okay? They have a relationship, and the relationship is this. If you're in the same relative position, for example, this bottom, or over here, to the right, or up. Right? Sometimes it's, left and down. Whatever it is, if you can find the angles that are in the same relative position, those are called corresponding angles. Doesn't mean that their measures are related in any way, but they are corresponding angles. They correspond to each other. Then here you've got the interior between the two lines and the exterior here outside of the two lines, and also over here, right, on this side, outside of the two lines. And if you're in the interior, you could have two angles that are on the same side, or that are on opposite sides. One at each intersection. Not the same intersection, because they already have a relationship. But these would be alternate interior angles. These would be alternate interior angles. These would be same side interior angles, and so would these be same side interior angles. If I tell you that this angle is congruent to this angle right here, it tells you a bunch of other stuff too, because we know the vertical angles are congruent here and here, and we know that the linear pairs are supplementary here and here and here and here. And the thing is, if this is supplementary to this angle and this is the same angle, the supplementary angles have to be congruent as well. So if I just tell you that one pair of corresponding angles are congruent, I have also told you that the alternate interior angles are congruent, the same side interior angles are supplementary. Doesn't matter which one of those three I tell you, it describes a situation where there is a close relationship between the measures of these angles. When that situation occurs, it means the lines are parallel. And it goes the other way too. If the lines are parallel, then you can fill in the angles, because it means the same situation, the parallel line situation, is going to exist. This is what's going on right here. You've got two parallel lines and a transversal. This is 80 degrees. And because these two lines are parallel and this line is a transversal that crosses them, it means the corresponding angles are equal to each other. So this is 80. And if I look at this and I say, okay, A is equal to 80 degrees because angle A is corresponding with the 80-degree angle, that's not enough, because just because they're corresponding angles doesn't mean they're going to be congruent. They're congruent if they are corresponding and the lines are parallel. And you have to write that, or it's wrong. Then you can come over here and say C is 100 degrees because it's a linear pair with 80 degrees. And then B, which is over here, you'll notice this is now a triangle. We know this angle and this angle. The three angles together have to equal 180 degrees. So if this is 100 and this is 65, they add up to 165 degrees. What's left if we subtract that from 180? It's 15 degrees. So B has to be 15 degrees because of the thing called the triangle angle sum theorem. Do you have to remember those words? No. Can you just say to me, hey, the three angles have to add up to 180 degrees? Yes.
So, I'm confused. How did you get C1 100 again?
Well, if this is 80, right, because the lines are parallel and these are corresponding angles,
Yeah.
these two are a linear pair. So they have to add up to 180. They are adjacent angles, and the sides that they don't share form a straight line. So these two angles added together have to be 180 degrees.
Oh.
This one's 80.
Yeah.
That makes this one 100.
And you just add 65. You already gave it to
100 plus 65 plus B has to equal 180. Okay? This has to do with determining whether or not triangles are similar. And what I want to do is I want to give you basically a flow chart that tells you exactly what to do. If you're given two triangles and you're asked, are they similar? The first thing you want to know is, do I have all 6 side lengths? If the answer is no, you can't use side-side-side similarity. You don't have enough information. If the answer is yes, then what you do is you take the numbers from triangle 1, small, medium, large, and the numbers from triangle 2, small, medium, large. You make ratios out of them, and you check to see, are those ratios equal to each other? If the answer is yes, that's side-side-side similarity. Now, if the answer to this is no, or if you got this answer, no, you try something else. You look to see, are 2 pairs of corresponding angles congruent? Now, sometimes it's really easy. I could give you 2 triangles like this, and I could say this is congruent to this, and this is congruent to this, and then you would say, yeah, I got 2 pairs of congruent angles. Sometimes it's not quite that simple. Maybe I would give you this and say these 2 are congruent. Do you have another pair that are congruent?
No.
Well, here's the thing. These are really 2 different triangles, right? This one and this one. But they both share this angle here. And this angle is congruent to itself because of the reflexive property. So it's like having two triangles, one here and one here, where these are congruent and these are congruent here and here. And you do have 2 pairs of congruent angles. You just had to hunt for them a little bit. Or what if I told you this? I don't tell you anything about the angles, but I tell you these 2 lines are parallel. Do you have 2 pairs of congruent angles? Yeah. First of all, you still have the reflexive property for this one, but also, since this is a transversal crossing 2 parallel lines, the corresponding angles are congruent, and the same thing's true over here. The corresponding angles are congruent.
So wait, so how do you know that the top of it is a reflective property? Like, I don't get that. Like,
There's only one angle here, right? We agreed?
okay.
But it's being used twice. It's being used once for this triangle, and then it's being used again for this triangle,
Oh, okay.
right?
Yeah.
And there's a thing that says every angle is congruent to itself. Everything is equal to itself. and that's the reflexive property. So if you have two pairs of corresponding angles, if you can find two pairs of corresponding angles, then you have angle-angle similarity. If the answer is no, there is still one more chance. Do I have one pair of congruent corresponding angles and the measure of all four sides that make them? What does that mean? Well, it means this. If I have one pair of corresponding angles that are congruent, and I have this measurement, this measurement, this measurement, and this measurement, all four of them, then there's one more chance to show that these triangles are similar. And the way you do it is by taking from triangle 1 the large number and the small number, and from triangle 2 the large number and the small number, making a ratio out of them and seeing if they're equal. And if they are, then you have side angle side similarity. And if the answer is no, they're not similar. Because the only things you can say tell you that two triangles are similar are angle-angle, side-side-side, and side-angle-side. So now when it comes to a proof, the first thing you want to do is write down everything that's given. If the lines are parallel, you write that down. If the side lengths are given to you, you write that down. If two angles are congruent, you write that down. Why? Because as you go down this way, you want to make reference to that. If you want to say, I've got proportions, AB over DE is equal to BC over EF, well, you better tell me what those numbers are up here. Otherwise, what are you talking about?
So how would you do that, for example?
Well, up here, if you had AB is equal to 7,
Okay.
and I don't know, BC is equal to 3, and DE is equal to 21, and EF is equal to 9. Okay. If that's here, and then you write this, I can see that, yeah, you're right. When I put those numbers in, those are equal. If you don't write this first and you tell me these are equal, I have no idea what that means or how you know. Something else, by the way. This symbol means similar. Triangles can be similar. Angles, lines, sides, points, those cannot be similar because it makes no sense. Similar means same shape, different size. Well, if the angles are the same shape, they're the same size. And all lines are the same shape. The sides of triangles are the same shape. They're lines, line segments. The other thing is you're not trying to show that the sides are congruent. So you would not want to say, well, look, AB is similar to BC. No, that's not it. And you don't want to say AB is congruent to DE because they're not. Bottom line of this is, when you come to the end, if you decide that triangle 1 is similar to triangle 2, the only thing that you can put here that will make sense is one of these. If you decide that two triangles are congruent, you can put this here, you can put this here, you can put this here, you can put this here. You got 5 choices. You can put this here.
top one is for similar, the other one's for congruent.
Right. And it goes the other way too. You can't use these to prove anything else. So if I say, well, angle C is congruent to angle D, how do you know? Well, angle similar? No. You can only use that if you have two similar triangles that you're saying are similar. Okay? If you're using side similarity, you better have shown me 6 side length measures and the fact that 3 of those pairs of side lengths have the same ratio. If you're going to use angle, you better have shown me that there are 2 pairs of congruent angles. If you're going to put SAS, then you have to show me that you have 2 angles that are congruent, and then you had all 4 side measurements here, and when you put them into ratios, they were equal to each other. Having said that, now we're looking here. Do I have all 6 measures?
Or, A?
Yeah, this one. Right. It's a yes/no question. Do I have all 6 measures?
Yeah. No.
No. So I cannot use side. Do I have any angle measures? Yeah, I know that angle A is congruent to angle A. Do I have any other angle measures? Nope. Okay, so I have this one angle measure. Do I have the side lengths of all 4 sides that make up that angle? What's the matter?
Also.
You're having trouble with there's 2 different angles there?
No. I see the 2 different angles. But on the other one, on the example, you put that there was a traversal.
Yes, but that was because the lines were parallel. Here we don't have
They
that.
don't show that. Okay.
Okay. Here we got A, U, S. Right. These 2 angles are congruent. I know that this is 12. I know that this is 9. And although it's not exactly given, I can calculate that this is 16 and this is 12. Because 12 plus 4 is 16 and 9 plus 3 is 12. So if I take the small one over here and relate it to the small one over here, and I take the large one over here and relate it to the large one over here, and then I reduce these fractions, this is 4 over 3, and this is 4 over... Hey, these are equal. So now how do I write that as a proof? First thing I do is write down everything I'm given. AP equals 12, AL equals 9, PU equals 4, LS equals 3, and PL equals 15, given. Now that's not exactly what I need. What I need is AU, and that's going to equal AP plus PU, which is equal to 16. And I need AS, which is equal to AL plus LS, and that's 12. Basically, all I'm doing is segment addition. I'm adding the segments together. Now I'm going to take the big one from here and the big one from here, AU over AP, and the big one, the little one from here, and the little one from here, which is AS over AL. And I'm going to say that those proportions are equal because this is equal to 12 over 9. And this one over here is equal to 16 over 12. We just showed that those were equal proportions. Am I done? Not quite. I can't use side angle side yet because I haven't said anything about an angle. But I actually know that angle A is congruent to angle A because of the reflexive property, which means now I know triangle APL is similar to triangle AUS because of side angle side similarity. And that's what the proof looks like. Now, since I know that the ratio is 4/3, right? This here is the ratio. That has to equal x over 15.
Oh,
Okay? Because that's the definition of triangle similarity. That's what it means for triangles to be similar. All the ratios are the same. So x is equal to 15 times 4/3, which is equal to 5 times 4, which is equal to 20. Okay?
so you basically just divided 15 and 3,
Mm-hmm.
which gave 5.
Mm-hmm. This one, I could play around with the side lengths, except that I don't really have enough. Well, I certainly don't have 6, and I don't have 2 on this one. So I would need 2 here and 2 here to be able to do side angle side. The only thing I can do here is to compare angles. 27 and 27, I've got one pair of angles that's congruent. 54 and 95, they're clearly not congruent, but maybe if I added 27 and 54, I'd get, what, 81? So that would make this 99. Oh, this is 95. These are not similar triangles.